Now, where's my physics? Physics. Doo-doo-doo. I have some. I don't know. I felt like typing up some slides for this lesson. So I have some slides for this lesson. But the reason is there are a few definitions. So I want to make sure you have good definitions for this topic. There's not really much maths. Well, I mean, there is maths in it, but it's not too difficult maths. I want to make sure you understand the words and the ideas. Okay. Right, so we'll start. He left. Yes. He left. Who's this? Hey, you talk to me or them?
You very quickly.
Don't go anywhere.
They went to the church and we'll never say it again.
Because he chose the university different for you.
Yeah, very good university. No. Cambridge is a big fucker. You forget Stanford. But Harvard is, you can say.
Harvard University.
Yeah. And you say UK.
So where is that?
USA.
Stanford is good, but better than Harvard.
No. That's okay.
Yes, okay. Harvard and Oxford. Yes.
Hong Kong University.
No, that's okay.
Yeah, it's a top university in Asia.
Really?
Yeah. University of Hong Kong.
It's such a good exam.
But highest rank is in Asia is Tokyo University.
Okay.
Japanese.
No, that's what I'm talking about.
The worldwide or just Asia?
Worldwide.
Worldwide. Okay. Yeah.
Where's that?
Okay, I don't know.
Yeah, that's the part.
Yeah. Actually, first we need to find a way to talk to the leader of North Korea.
That's one way to read.
Okay.
And then we specifically.
But in lab with the resources. And when it's resource, we need long to get the program.
We'll do
Yeah, the biggest, the famous one, the most famous lab in the Europe, what's that called? You know? It's the cell? I don't know.
This is the thing. I think this is during this enough to make it.
So what's our first aim? from Denmark.
Denmark, yeah.
Yeah, in the Second World War. Very Second World War.
Denmark?
Yeah.
Why? Russian.
Yeah. So who follow here?
Yeah. Denmark, why? They
So in Second World War. Yeah. From their country, they have the luxury. Well, Germany, they but Denmark, they now they at present time very the math, Ross.
Sorry about that. Sorry. Student problems. I won't say.
What kind of problem?
Complicated problems.
Time.
One of many problems. There's a list of problems with this student. Okay, where's my full screen mode? So we are going to look at nuclear decay equations. So that's the title, if you want to write that down. What does the word decay mean? Decay. Yeah? Yeah, disappears, goes away. Yeah. Okay? Alright. So there are two things I want to have a look at. You don't need to write this down. I want to look at decay equations and what things are conserved in decay. So anyways, on to the definition. What am I talking about decay? So you'll need this. So I'll just read it first. No, you can write it in a minute. I'll read it first. I want to make sure you understand it. So radioactive decay, also known as nuclear decay, or radioactivity, which is the name on the worksheet, is the process by which a nucleus of an unstable atom loses energy. So you need to imagine you have a nucleus and it's losing energy. Okay? By emitting radiation. And there are three types of radiation. The three types are alpha, beta, and gamma. These are the three types of energy, three ways the energy can be released from the nucleus. Okay. You think about in chemistry, sometimes an electron might be released. What is this called? When an electron is freed? Ionization. So it's a similar idea in physics. We have a nucleus, but there are three different things called alpha, beta, gamma, which are released. Now in a moment I'll explain what alpha, beta, and gamma are, but first write this definition down. So this is for radioactivity. Now this is a very formal definition. For the exam, you could make it a bit shorter. For example, in the exam you could just say, radioactive decay is the process by which a nucleus loses energy by releasing alpha, beta, and gamma radiation. Alex? Yeah. Have you heard of this word before? Radiation? Yeah? Where have you heard it? You heard it in physics or?
I was watching different things.
Oh, documentary, great, yeah. Radiation, you know this word in English? No? And radiation, you know this word?
Yes.
Oh, you do? Where did you hear it? Oh, you translated, okay. Radiation, where might you see this word, radiation? Power plants, hospital. In the hospital, when they give you an injection, and then they put you in front of a screen, and they can see everything inside you. They put something inside you that glows. You know, have you ever done this in the hospital? No? It's like an X-ray, but it's a different thing to X-ray. Anyways, radiation in English and physics is you picture something dangerous. Radiation is a bad thing. It's unsafe. Yeah. Like, for example, Chernobyl. I'm sorry, I don't remember the names of the two cities in World War II. That's it. Hiroshima and Hiroshima or something, no?
Hiroshima and
Yes, that's it, yeah. He is an expert on it. Radiation is a bad... No, it's not bad, sorry. It's a dangerous thing. It's dangerous. So, I said there are three types of radiation. Alpha, beta, gamma. So let's look at each type. So, just for example, you don't need to write this down. Uranium-239 is an isotope. Uranium is radioactive. This means it will decay. That is, alpha, beta, gamma will be released from it naturally. But it does not do this forever. So things which are radioactive are only radioactive for some time, and then they're not radioactive anymore. Okay, so radioactive is it's a limited time. It's not continuous. Okay, so the first thing here now, alpha. Alpha particles are basically 2 protons and 2 neutrons. What does that make them? 2 protons and 2 neutrons? Helium-4. Yeah. Basically it's helium. So in other words, alpha is just a helium, but a special type of helium. Helium-4. 2 protons, 2 neutrons, no electrons. That's called alpha. Definitely this one. And this in the exam would be like a 1-mark question. What is alpha radiation? Or what is an alpha particle?
It's very cheap question.
What's that?
It's very cheap question. Almost too hard.
Hard? Hard question?
No.
Popular.
Popular, yes.
Popular? What word did you use?
It's
Ah! I understand why you use this word, but this is a very informal word. We do not use it like in this conversation.
Okay.
It's English.
No, it's not Chinglish. It's just an informal English word. Yes, this topic is very popular in the exam. In fact, I think this is on every exam paper. It's very common in the exam. It is a hit question, yes. Okay, next now, you have this? The next one is beta. Beta particles are very fast moving electrons. That's all a beta particle is. It's a fast moving electron. In fact, I don't really even need to say high energy, because if it's a high speed, it's also a high energy. What type of energy will it have if it's high speed? So in fact, I could have just said beta particles are high speed electrons.
A high energy electron.
Or high energy electrons, yes. Right, our third type of radiation is gamma radiation. Does anyone know gamma? Yeah, gamma radiation is different to alpha and beta. It's actually a wave. So also known as gamma rays. And they're electromagnetic waves. Most importantly, key word here, high frequency. In fact, I should say very high frequency. Very, very high frequency waves. Okay, do you have that? Yes? Can I go to, I want to draw out something for you. Hang on. Whoops, there's my paper. There's my paper. So this is, oh no, my pad is not working again. Well, I've done a draw, but what I would like you to do is to copy this into your notebook. But before you copy it, I want to explain what's happening here. Can you see, Abraham? So this is your nucleus, and it's not stable. There's radiation coming off of it. And here are the three different types. This is alpha. It is 2 protons and 2 neutrons. This is beta. What's beta? Electron, and then this is gamma. So this all comes out. Now all of these are bad for you. They'll make you sick. Okay? The alpha particle, you can actually stop it with some cardboard. Like some paper will stop it. So if I have some alpha radiation and you want to be safe, if you just put even some paper here, it'll protect you. Okay? Beta is more difficult to stop. You see, you need something like aluminium to stop it. And aluminium. The metal, yeah. Sorry, if you're American, you will say aluminum. Yeah. And then the last one, gamma, is the most difficult to stop. You see, you need like lots of lead. Lots of lead to stop it, like maybe 1 meter. Lead, Pb. It's in chemistry. Lead is this symbol, Pb. It's where would you see lead nowadays? I was going to say on your shoe, but shoes aren't lead. But lead it's like this material, and it's very, very, very dense. It's very dense. So when gamma tries to hit it, the lead stops it because the atoms are so big and tightly packed together. So lead is, what's like lead? Something really dense. Yeah, plastic's not so dense. Plastic, nah. High density. Don't forget high density.
The small black hole.
Yes. I think if you were near this, you would have other problems. Anyway, I'm sorry, I can't think of where we see lead nowadays. Lead. Old pipes in old buildings use lead. Maybe 100 years ago, lead was used to make pipes in buildings. And then people stopped doing that because lead is bad for your health. too expensive.
That can stop the worm.
Gamma can? No, I don't think so, because gamma is a wave, like a light wave. So it will just pass through the diamond and maybe change its direction.
And you can change direction also.
Well, if you have it correctly positioned, yes. Yeah, I suppose so, yeah. Now, so you can see that gamma goes the most. However, there's an opposite side to it. The alpha has the most energy in it. So if alpha particle hits you, it does the most damage. So like the alpha, beta, gamma, the gamma can go through most. But the good news is gamma is the least dangerous. It has the least energy. Okay, and this is actually good because gamma is around you all the time. It comes from space. So there's actually gamma everywhere. And the higher up you go, like in a plane, the more gamma radiation there is. But the good thing is it doesn't cause much damage. Okay? Alpha is very dangerous, and in fact, if alpha was inside you, like if you drank some water that had alpha inside of it, it'll make you very, very sick and will kill you in a few weeks. Okay? So what I want you to do, I want you to draw this in your notebook, but also write down here most dangerous, dangerous, not too dangerous as well. Okay? Because in the exam, they would sometimes say things like, you know, what would happen, or why is alpha radiation, or they might say which one is most dangerous, or what would happen if you swallowed some alpha radiation, like if your food had it in it. The answer is it would cause your cells to be damaged. You know what I mean by cells? You know cells? No. It would cause your DNA to be damaged. DNA. Alpha, yes, that's the other thing. All of these here, the reason they're bad for you is they break DNA. This is why it's bad for you. And you need your DNA. It's not optional. So please draw this and write down most dangerous, dangerous, least dangerous. Now let me just get a pen so I can write on the board since my eraser's not working. Still drawing? Not too bad. Alpha, yeah. Okay, did you draw it?
Yeah.
Good job. Okay. What's that? Okay, well I'll just write my notes here. We'll talk a little bit more about alpha, beta, and gamma. So here is my uranium-239. Have you got your periodic table?
Yes.
Can you look up what the number, the atomic number is for uranium? Oh, okay, no, actually I have it here, I'll tell you. It's 92. So this is actually really uranium-239-92. Okay. Now, if I have my uranium-239-92, and if it's decaying, what happens if an alpha is released? So here it is, decaying. So what is alpha? What's alpha? Two protons and two neutrons. So that means you have some helium, isn't it? 4, 2. Correct. So this is my question. Will you still have uranium? No, because if 2 protons leave uranium, look at your periodic table now if you have it, tell me what you will get. If 2 protons leave, you don't have uranium anymore, what do you have? How many protons do you have in total? 90. So what is that? I believe you might be right, Abraham, but just confirm it, please.
TH.
Oh, sorry, not this time. TH is thorium, I think. Yeah. Or is it thorium? I think so. Well, I can look it up, but TH, thorium. So TH. So how many protons are in thorium? 90. Now, if the helium took 2 protons and 2 neutrons, it means it took 4 nucleons. So how many is left here for the thorium? 2, 3, 5. Now this is what I was saying last week. In physics, for us, the most important thing is this. That the total proton number here must equal this plus this. And the total nucleon number here must equal this plus this. So the tops and bottoms must be equal. Okay? This is what alpha looks like. Let's do beta. So let's imagine instead beta took place. For example. You know what? Actually, let me use something different now. Let's say thorium instead. Yes? What's wrong? Oh, because of this? Sorry. Thorium 9235 beta. So if a beta took place, an electron comes out. Now the electron we write it, maybe you might feel it's a little bit strange, but yeah. We actually write electrons in our formulas like this, a 0 and a -1. And the reason for that is to make it balanced. But if you want, you can think about it like this. Electron equals E0 -1. So here's one example. Here's another example. Yes. No. Now this is what I'm getting to. This is beta is very strange. When beta radiation takes place, an electron is released. But something very strange happens with the nucleus. So listen carefully. You're listening to? Listen carefully. When beta is released, something very strange happens here. When the beta is released, the nucleus gets, it changes one neutron into one proton. So that's very strange. It somehow takes a neutron and it becomes a proton. So instead of being 90 here, what will it be? 91. But this will still be 235. Why is this still 235? Yeah, which is still the same. So, Abraham, can you tell me now what number 91 is? Or actually, you have it there. You guys have it. P-U? P-A.
Volcanium.
It's very complicated.
Volcanium.
Let's see it. Where?
Yeah.
Whew. Where is it? Protactinium. Oh. PA. This is still balanced, isn't it? It's still total 90, yeah? And what's the last one? Gamma. So let's do PA as an example. If PA releases a gamma, no problem. It stays the same. Gamma is just a wave. It has no protons or neutrons, so it's the same thing. Now this doesn't really, I'm making it seem very simple. Usually what happens is, at the same time you get these. It all happens together. In my example, I have it almost like first alpha, then beta, then gamma, but that's not what really happens. What really happens is alpha, beta, and gamma come out at the same time. Now, let's have a look at another example here. What do you think this is? No protons and one neutron. What's this? If it has no protons and one neutron, it is not a trick. It's a neutron, isn't it? Yes, of course. No protons and one neutron. It's a neutron. If I have uranium-238 and I fire a neutron at it, I want you to tell me what I have here, plus gamma. So what goes in here? So how many protons will I have? How many protons will I have? 92. And how many protons and neutrons?
239.
Yeah. What element is this? Still uranium. Okay, let's give you another one. You can try this for me. PO 21484. That releases an alpha. Alpha is He42. So I want you to balance this equation. What goes in the box? You'll need your periodic table. What is it? Lead? Pb. Pb. What goes up here?
210.
And here?
82.
Let's do a difficult one now. Let me find a difficult one. Yes, a difficult one. So, I'll need a periodic table. Let's see. to reduce by 4 and add 3. Okay, so I'll have uranium 23992. And in this one, alpha and beta are released. So here we have uranium sorry, not uranium, sorry. We don't know what it is. I'll call it 86. And then no, not 86. I'm so sorry. Teacher's getting confused. 2, 4, 6. 246 and add 4, 8, 12, 2, 2, 7, 88, yeah. Actually, what is 88? 88 is radium, or A. So I can actually write in or A. Or A. So in this example here, so I don't need this anymore. I hope I did these numbers correctly. In this example here, uranium turns into radium. Alpha, beta, gamma are all released. So alpha, I'll write here. What's alpha? Helium 4, 2. What's beta? So E0 minus 1. And gamma? Gamma. But I don't tell you how many alphas and betas and gammas are released. So you don't know how many alphas and you don't know how many betas. And I want you to find the x and the y for me. So we'll do it together. So, what should I do to solve this? What should my first step be?
You need to balance the equation.
Yep. So the second step.
Second step, two right equations.
Yeah, so look closely. What should I write?
2x.
2x? 2x, yes, okay.
Minus y
Minus y.
equals 4.
Let's try something else.
Okay. 5.
Let me help you. Look, 92 should equal 88. You're right, but I want to make it clearer. 88 plus 2x minus y. And 239 should equal, you tell me?
4x.
No.
250.
Yeah,
Plus 5.
plus, I'll write there, 0, y. How many equations do I have here? 2, and how many unknowns? 2. And you've seen this in semester 1. So please find the x and the y for me now. Yes. Yeah. X is 3 and y is 1. I'll give you a minute to finish it. So can you see, believe it or not, that's actually a difficult example for the exam. So this question, balancing these nuclear equations, they're actually quite easy in the exam. And you have lots of examples in practice that are quite short. Now, I have some other things to say, but I don't want to forget to tell you. If you just look at question 1, there's, I think, just one thing missing on the right in each example. You see what I mean here, Abraham? Like, there's just one thing missing on the right. Yeah? In number 2, I don't know, I think there's, again, I think there's one thing missing on the right as well. Yeah. I don't know why they give so much space here. Can you see here, Louise? Or you finish it? In number 1, there's something missing on the right. So, for example, in the first one, I did the first one. It was this one here. I did. Yeah. And then I think I did the second one here. The one with the PO in it, did I? Yeah. I did that one there. Okay. And then number 3 is my own example, but what I just did there, where you have to find how many alphas and how many betas. That's my last example there, the one you're doing now. Okay, did you get that, sorry, Abraham? Yeah, so one thing missing, and then this alpha and beta, so 2 things missing. So actually, this is the difficult one, and I hope you can see it's not really difficult. Now, this process, if you look here is my uranium, and then afterwards, what do I have? I have Ra, I have, what did you say here? It was 3, wasn't it?
Yes.
So afterwards, I have 3 alphas, which are just helium, and what else?
1
And then 1 electron. So my question, what things do you expect to be the same here and the same here? So for example, if we think back to mechanics, what's the same at the start and what's the same at the end? Energy at the start and at the end should be the same. True. What else? Momentum also. Momentum at the start equals momentum at the end. Anything else? You know something? No. We think it should, but it's not for this. Just for this though. The charge. For example, my uranium has no charge. So what should the total charge afterwards be? Also 0. Okay. So there are 4 things which don't change in a process like this. Firstly, energy. The total energy is the same. Momentum. Also, what's going on? Why?
Turn off.
I didn't turn it off though, it turned itself off. Well, you can write the 4 down. Energy, momentum, charge, and there's one more. Come on. There's one more that doesn't change. So we have 3. Energy, momentum, charge. And the last one, you're going to see it now in a minute. Better hide it. Come here. Why did I say these are equal? For example, why does 92 equal this or 239 equal this?
Same.
Yeah, why? Why is the same?
mass,
Not mass, no?
atomic number.
Yeah, this atomic number here must equal the atomic number here. Yes? And what's this one called? This is the this is the mass number. So the mass number must stay the same, and the proton number also does not change. So we call that the nucleon number. Oops. So these are the 4 things that stay the same. And this could be something you get in the exam for 4 marks. The question might say, what are the 4 quantities that are conserved in decay, radioactive decay? And you get 4 marks, and it's 1 mark for each of them. You think, You think the mass should be the same. In fact, it's not. It's quite strange. And we'll see that, we'll see this in a later class. But these are the 4 things which must not change. Now, this is why I want you to think about your chemistry. Because if this was in chemistry, you would say the mass. Wouldn't you say the same? Or at least the number of, for example, you'd say the number of uranium atoms would stay the same, and the number of radium atoms would stay the same. Like when you have your H2 plus O equals H2O. How many hydrogen? 2. How many hydrogen? 2. So you're basically saying that the mass stays the same. Basically. And this is not true for this in physics. In fact, the mass will always be different. So this is quite strange. So mass is not on this list. It is for chemistry. If this is chemistry, we would also have mass, but it's not, so we don't include it. Okay. Now, these questions are very, very short, so you should have no problem doing them all. They're very short questions, right? But I would like you to do them all, because these questions are on every exam. Well, nearly every, like 95% will have one of these. In section A, or section B, or sometimes both. So it's a good question for the exam. Yeah? By the way, we have physics tomorrow morning. Yes? Yes. I recommend not being late. Because Emer will be joining the class.
Why?
She wants to see a physics class.
For what? You want to start to study?
Yes, that's the reason. She wants to study radiation. She'll be in the class. So, my advice is don't be late for this class. Yeah? Because there's only 3 of you. Yeah. Okay. I don't think there's any questions. So what we're going to do tomorrow is continue with radiation, and we're going to look at the graphs. So remember at the start I said this is not forever. The radiation is only for a limited time. So we're going to look at the graphs here. We're going to see it decreases. It gets less radiation. It doesn't continue forever. Of course, it can't continue forever, because look, how many protons did I lose here? 4. So if I keep losing 4 protons, can this continue forever? No, it can't. I have to stop. So that's what we'll look at tomorrow. Okay? Alright, we'll finish there. Are you going to
Chemistry.
go back to that room? Yeah.